Adilson de Oliveira to present his talk, Magnetic and Magnetostrictive Behavior in Multiferroic Composites, Influences of Dimensionality, Magnetic and Electric Fields.
Good afternoon. Thank you for organizers for inviting me for presentation these results. These results is a collaboration of many colleagues from physics department at Federal University of São Carlos. And many years, this group studied different properties of multiferroic composites, and they study effects of the magnetic and electric fields and the dimensionality of the particles, these composites. My talk about is a quickly show of multiferroism, the main subjects of this workshop, this effect of the magnetoelectric susceptibility, and this magnetoelectric effect in particular in composite materials. This effect is associated of magnetostriction and magnetoelectricity, and show this model for describing this effect of the magnetostriction and magnetoelectricity in composite materials. Well, this multiferroism is a different ferroic orders in materials, in particular in the magnetoelectricity associated of the magnetization and magnetic properties of the ferromagnetic or ferrimagnetic materials and effects of the piezoelectric and ferroelectric materials. So this connection of the three properties is associated in magnetoelasticity, particularly magnetostriction effect. Is produced of different effects, in particular magnetoelectricity. So it's very important to apply in different devices, different materials. In the possible approach for describe the multiferroism is approached by from free energy. When show free energy of the system, show present different components associated of electric field, magnetic field, this effect of the magnetic, electric, and cross effect of the magnetic cross electricity and vice versa, and different orders. So, it's possible to define of polarization of the system of first deviation of the from energy for electricity is many terms, or from magnetization is deviation of this many terms. And possible to define of the spectral tensor associated of the permissivity and electric permissivity and magnetic permeability. This name of the magnetic electric susceptibility tensor. This magnetic effect in composite materials is associated of the electric effect and mechanical and magnetic. The cross these properties is produced of the effects of magnetoelectricity. So the polarization is possible to define in function of the strain and in function of the temperature, and variation of the polarization in function of applied magnetic field is possible to describe this form. So it's possible to define the deviation of polarization in function of the strain is a piezoelectric coefficient, and deviation of the strain in function of applied magnetic field is magnetostrict coefficient. The combination of this coefficient is a variation of the polarization in function of the applied field in fixed temperature is possible to describe of coefficient of magnetoelectric coefficient is product of direct of the piezoelectric coefficient magnetic strictive coefficient. However, it's important to include of this ad hoc, this coupling factor associating of the interaction of the part of the sample is ferroelectric, a part of the sample is ferromagnetic. So the emerging of the magnetoelectric effect is dependent of the piezoelectricity and the magnetostriction. Magnetostriction is an old phenomenon observed by Joule in 19th century. When applied a magnetic field, the magnetic material change of this size in this direction, increase of, for example, the length of this material. Magnetic striction is the point of view of the magnetic domains. Is dependent of the apply of magnetic field is a change magnetic domains in direction of the easy axis of magnetization. When increased magnetic field, the change of the direction of the magnetic domains. And finally, is a dependency of this. Del L is proportional to a magnetostriction coefficient. Depending this formula, depending of the angle of the direction of the expansion and direction of the magnetic domains. This expression is valid for a polycrystalline materials. In the single crystal is more complex because this is a tensor. So, this study in our group is based off this composite, PMPT and cobalt ferrite, and PMPT nickel ferrite. This material is a composite, this is a polycrystalline, and the grain points is a ferrite, or cobalt ferrite or nickel ferrite. Is studying of the samples is proportional 20% of the ferrite and 80% of in mass of the PMPT, and a good density around the 96% of quality of the sample, and guarantee of the possibility of the polarization sample. If you not a good density, sample is not a good polarization. Magnetic measurements, magnetostriction measurements is very easy to perform. Use a capacitive cell. When applied field, the sample change of the size and the change of this distance of this plate of the capacitor, and the associate of the capacitor to expansion of this material. And the magnetoelectric effect is possible to measure to apply a AC field in the sample used by a locking, and use a DC field applied in the same time. The AC field is induced of the movement of the magnetic domains, and the DC field is a change of the magnetization of the sample. So, it's possible to obtain this curve is a typical curve of the PMPT nickel ferrite, and the red curve is observed a magnetoelectric coefficient, and in the blue curve, magnetostrictive coefficient. It's a very interesting, the same, in the maximum of the magnetoelectric coefficient is a same position of the minimum of the magnetic restriction. So this result show is a direct coupling of this magnetic, ferromagnetic phase with ferroelectric phase in this material. If you study of the magnetoelectric effect as a function of the angle of the polarization of the sample, is polarization sample around 2 kilovolts per centimeter, is observed of the change of the values of the magnetoelectric effect in function of the field, the angle. So is a maximum in the 0 and 10 degrees is absolutely the same, and the decrease is a change of the signal of the magnetoelectric susceptibility. The configuration is the electrical polarization of the sample and the change of the direction of the sample, the change of position of the sample in function of applied magnetic field. It's a very interesting, the same behavior, this behavior is exactly the same behavior, very quite same behavior expected by a magnetostrict effect. Yeah, is using the same expression, 3/2 cosine of x minus 1/3 minus d. is needed to increase, is ad hoc these two constants because it's not directed, because of the coupling of this phase, ferromagnetic and ferroelectric phase. Is a direct action of this, the electric polarization of the sample, and the magnetoelectric field is a connection of this magnetization. These magnetic fields at which maximum minimum value of the magnetoelectric effect occur associate of the magnetostrictive property of the ferrite phase. This dependence of the magnetoelectric coefficient shows an isotropic behavior in function of the applied magnetic field and your direction in respect of polarization vector. Okay, this is a connection of the magnetostriction and piezoelectric effect is very important to understand the next step of our study. The study of the effects of the in low temperatures of these properties. From Gibbs energy formulation, it's possible to explain of this tensor is a function of the magnetization and the piezomagnetic coefficient and the strain of the sample. It's possible to explain magnetostrictives in function of this tensor. First, in the first approximation is a relation of this stress of the sample associated with square magnetization. It's a very common to apply, for example, a polycrystalline materials use a Curie group for describe this tensor, and you obtain this expression associated of the strain of the sample of a square magnetization. However, in case of the ferromagnetic materials, is a very important to consider of the piezomagnetic effect associate, oh my God, associate of the this characteristic of the spin orbital coupling, in particular in cobalt ferrite. This uses the same symmetry is obtained this tensor and apply in this expression, obtain of this expression quite different, not only square magnetization, but depend of the magnetization and the susceptibility of the sample. So this coefficient of magnetostriction is a difference of this tensor. It's possible to describe this form. So when you apply this model, for example, this magnetization as a function of applied magnetic field and the 5K and the 300K, this is a curve, it's possible to obtain direct of the magnetization curve, direct the magnetostriction behavior. So this is in the square is a direct measurement of the magnetostriction coefficient. This green is apply of this model, and the blue is apply a square model at 5K. This apply direct of the ferrite samples. However, when you apply this effect, this model in composites, it's a very important to consider this point. When apply magnetic field, this grain of the ferrite is change of the size and the apply of the pressure due to an environment, ferroelectric environment of this grain. Is a change of this characteristic of the magnetostriction of the sample. So it is including more one component associated of the elastic constants, similar to Hooke's law. The sample is applied magnetic field, is a change of the size of the ferrite grain, and this so is a force the force associated of the environment, ferroelectric environment. And they include a new term associated of the stress. And they use the same matrix and they obtain more complex expression. And the magnetostrict coefficient appear on 3 and 4 terms associated square magnetization, and the other terms associated of a remanent magnetization and saturation magnetization. This is a stress magnetization model. When apply this model in this sample, in PMPT, sample is observed in room temperature. The square model is a deviation, but in my model, this model is a stress model, is more adjusting, very clear in high temperature and low temperature, this component. So it's important to consider of this particular of the magnetostriction for understood magnetic electric effects. Okay? This model is very simple. Describe is a good agreement magnetostriction phenomenon in system 03 multiferroic magnetoelectric. And include of the Hooke's law is important to describe these effects. The next step is described by a magnetoelectric effect, in particular, the dynamics effects, the function of the frequency of AC field. So this is a magnetization of in different temperatures, 5K to 300K, and the magnetostriction and the same temperatures performed for this sample. So this observe of the magnetostriction as a function of the temperature and a function of the frequency is at 10 Hertz and 1000 Hertz. Observe of the room temperature, the behavior is very similar to observe expected for a composites. However, when of decrease the temperature, this is a very important change of this behavior of the magnetostrictions. Is a very strong transformation associating not only a change of the size of this material. Remember, it's a two different materials, a ferrite and piezoelectric materials, a different thermal expansion coefficients. It's possible not only the change, but only the response of this magnetic electric. So, when observe this expression, these terms, the constants and the polarizations, in principle, not independent of magnetic field. This only depend magnetic field. These are magnetostriction coefficients. When calculate of this magnetic restriction, appear of this term associated of the deviation of magnetization as a function of the applied field. This is a susceptibility. What's susceptibility? Because when performing the measurement of magnetoelectric fields is apply a AC field, and the dependence of the frequency is a very important. So, okay. So, the magnetization of the ferromagnetic component of this composite is possible to describe, in my proposal, describe of the part of magnetization associate a interaction of the spin lattice, and other part, no spin lattice. And the calculate of the effect of the deviation of the magnetization of the spin lattice is dependent of this frequency type of Colli-Colli model. This is a type of the spectrum of the relaxation system. And possible to describe this magnetization of the difference of this function of the susceptibility depend of this model. And first, I propose of this part, this adiabatic process and the isothermic processes associated of this susceptibility. So it is a susceptibility of associated of spin lattices. It depends of the isothermal susceptibilities, direction of deviation of magnetization in function of field, and chi prime. Chi prime is a component of real component of the AC susceptibility. Is depend of the frequency. So is calculate of the magnetoelectric susceptibility use this expression proposed by composites, and proposal of this susceptibility is this form for describe this effect. So compare of this AC susceptibility as a function of magnetic field. This AC susceptibility in 10 Hz and 1000 Hz is very different of the DC susceptibility. Is a magnetization, deviation of the magnetization as a function of the field. These are very different. This obtained direct of the magnetization curve. This obtained by a AC susceptibility direct technique using 1 orsat and the 10 Hz and 1000 Hz. When apply this model, this obtained of the very good agreement of the in 10 Hz and 1000 Hz, the reproduce of the curve. In case of the low frequency, observe is a very quite strain. Deviation of the strain is blue, is very close to the shape of the magnetoelectric coefficient. And high frequency is obtained this curve. Is not good agreement because probably my sample is not absolutely polycrystalline sample. It's not a homogeneous, perfect homogeneous distribution of the size of the grain in the sample. Idea is this effect is associated of this. Magnetoelectric composite is make grains of magnetostrictive, ferromagnetic material, and a piezoelectric environment around of this grain. This, when apply magnetic field, the magnetic energy is coupling of a spin system via magnetostrictive effect, and appear a process of the spin lattice relaxation associated of the ferromagnetic phonon lattices and ferromagnetic phonon lattice bath, because it's 18% of piezoelectric material in compare of the 20% of ferromagnetic material. This coupling produce of the electric energy appear by is effect of the change of the size of the grain, is make a pressure of the ferroelectric environment, and produce via piezoelectric effect produce of the current in the sample. However, is interesting results is a PMPT is a cobalt ferrite shows a clear dynamic. However, in PMPT nickel ferrite, this dynamic is not observed. Observe of the change of the frequency, the 10 Hz and 1500 Hz is a clear dependence of this frequency. Above 100 Hz is a change of the behavior. In case of the nickel ferrite composite, is a 10,000 Hz is not changing significantly the shape of this electric field. What's the difference in the nickel ferrite and cobalt ferrite? The difference is associated of the spin orbit couple. Nickel ferrite and the cobalt ferrite is in a spinel structure, but the cobalt ferrite is a strong spin orbit coupling by a cobalt, and in the case of the nickel ferrite is not exhibit the same behavior. So, in this process, it's possible to two processes occur when apply AC field in the sample. In a limit of the low frequency is isothermal processor observe this behavior of magnetoelectric effect, and show increase of the frequency is change of a diabatic process of the sample. Is a change of the level of the equilibrium of the state. In case of the isothermal system, is a density of the population is make an equilibrium of like a Boltzmann function. So, and or increase the frequency, the change of the levels and the state in the equilibrium state is a difference. Is associated of this when of the increase omega tau is more of 1, is a change in this process. This magnetoelastic effects is very important to a difference of the total angular moment and the spin orbit couple in case of the nickel ferrite is a no. For check of this idea, I perform a magnetization as a function of applied magnetic field and different rating of the fields. And the black curve is an equilibrium, is applied magnetic field, stop at 10 seconds and measure magnetization. In the other case, is perform a 100 Oersted per second of the sample. Is observed a clear is a difference in cobalt ferrite curve, PMPT cobalt ferrite curve, is a difference of this situation. And the nickel ferrite in the 100 Oersted per second in equilibrium condition perform the same result of the magnetization in function of the fields. So, in the presence of the EC magnetic field, the electrons relax to the high energy level and not contribute, do not contribute to magnetostriction. In this condition is a metastable, and the electrons return to initial condition after spinlet's relaxation time. Consider one period of the AC magnetic field measurement is a frequency high enough, only part of the system contributes of magnetoelectric effect. Remember, if the perform magnetization 100 Oersted per second equivalent of 100 hertz of this magnetization. My final remarks about this, use this adiabatic assumption of magnetic susceptibility is proposal of the ferromagnetic and the ferroelectric phases are coupled by interaction of the spin of the ferromagnetic phase with composite phonos of spin-lets relaxation. This approach assumes the no spin-lets and susceptibility, spin not coupling with the lets, decrease of the spin-let susceptibility. The magnetoelectric effect in composite is correlating of dynamic spin-lets interaction of the ferromagnetic phase. This dynamic impact of the modes of oscillation, this composite phonon, causing a displacement of equilibrium position of no center symmetric ions induce variation of the electric polarization as a consequence the magnetic electric effect. Okay? Thank you for your attention and acknowledgement of FAPESP and the CEPIDES, CNPq, and international collaboration CAPS, COFECU Brazil, and France. Thank you very much.